This is an introduction to fractals. True or false? A fractal is always perfectly self-similar. False, sadly. Perfectly self-similar shapes fall within the category of fractals. However, not all fractals are perfectly self-similar, i.e. the coastline of Britain. It is slightly self-similar in that you can keep zooming in and you still have some amount of detail, even as you zoom extremely far in, kind of like illustrated here as you draw five points. However, it's not perfectly self-similar. It is somewhat self-similar. Then what is a fractal? A fractal has a fractional dimension, which is where the name comes from. Line is one-dimensional, square is two-dimensional, cube is three-dimensional. Then a fractal could be 1.585 dimensional. The dimension can be calculated discretely. This doesn't work for all fractals, but the thought process illustrated here works for perfectly self-similar fractals. Non-perfectly self-similar fractals, they use a different box counting method. So consider, if you shrink down an object by 1/2, like all of its dimensions, how much does the length, area, volume, all codified under measure, decrease by? So for example, if you shrink a line by 1/2, its measure or length goes down by 1/2. For a square, it goes down by 1/4, and a cube, it goes down by 1/8. And these scaling factors can be written as powers of 1/2, and the exponents are their dimensions. So a line is 1/2 to the first, it's one-dimensional. A square is 1/2 squared, two-dimensional, and 1/2 cubed, three-dimensional. Okay, so the Sierpinski triangle, a fractal. If you shrunk it down by 1/2, what would its measure decrease by? We can notice is that this little triangle here is the whole thing precisely shrunk down by 1/2. And you can kind of just like see it here. It's like this cut in half and it's this cut in half. So, and we can see that the scaling factor is 1/3 because in this like 1/2-ish triangle, constructed the original using 3 of them. 1, 2, 3. Therefore, the scaling factor is 1/2, and thus the dimension is 1.585. And there are some other interesting fractals. Newton's fractal is a family of fractals that essentially come from Newton's method of finding roots on the complex plane. And the Mandelbrot set is essentially it is found from repeatedly applying a function over and over. In this case, z squared plus c, where c is some constant on the complex plane. And it also crops up in other fractals, like specific configurations of Newton's fractal. That is fractals.